Welcome! In this session, we'll explore LeetCode problem number 1660, correct a binary tree. This problem involves working with binary trees and detecting structural anomalies. We'll dive into the problem statement, analyze various approaches, and implement an efficient solution. Let's get started. In this problem, we are working with a binary tree that is fully binary, meaning each node has either 0 or 2 children. However, there's an additional leaf node that has been incorrectly connected to one of the nodes at the second to last level of the tree, which is the level just before the actual leaf nodes. Your task is to identify and remove this incorrect node so that the tree becomes a valid fully binary tree again. To achieve this, you should perform a breadth-first search, or BFS, starting at the root. If there are multiple incorrect nodes, you only need to remove the first one you encounter during this traversal. The input to the problem is the root of the binary tree, and each node in the tree has 3 properties: a value, a pointer to the left child, and a pointer to the right child. The output is the corrected binary tree, represented by its root node, after you've removed the problematic node. Let's look at the first example. Here, the input tree is represented as an array 1, 2, 3, null, 4, null, null, 5, null. In tree format, this looks like a structure where the root node has a value of 1, with 2 children, 2 on the left and 3 on the right. Node 2 has a right child, 4, and node 4 has an additional right child, 5. This node 5 is the incorrect node that needs to be removed. The output, after correcting the tree, is 1, 2, 3, null, 4. In tree form, this means node 5 is no longer present, and the tree is now a valid fully binary tree. To visualize the corrected tree, you can see that node 1 remains the root, with nodes 2 and 3 as its left and right children, respectively. Node 2 still has its right child, node 4, but the incorrect node 5 has been removed. The explanation for this correction is that node 5 was improperly connected to node 4, which is part of the second to last level of the tree. By removing node 5, we restore the fully binary tree property, where all nodes at the second to last level have either 0 or 2 children. Now, let's examine another example. The input tree is represented as 1, 2, 3, 4, null, 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 5. When visualized, the root node 1 has 2 children, node 2 on the left and node 3 on the right. Node 2 has a left child, node 4, and node 4 has an additional right child, node 5. This node 5 is the incorrect leaf node that needs to be removed. After correcting the tree, the output representation becomes 1, 2, 3, 4. In the corrected tree for the second example, the root node 1 still has nodes 2 and 3 as its children, and node 2 retains its left child, node 4. The incorrect node 5 has been removed, restoring the tree's fully binary structure. The explanation here is that node 5 was improperly connected to a null value at the second to last level, violating the rules of a fully binary tree. By removing it, the tree adheres to the required structure. Additionally, keep in mind the constraints of the problem. The tree can have up to 10,000 nodes, and all node values are unique. The tree depth will not exceed 1,000, but you should consider edge cases, such as small trees with just 2 nodes, large trees with depths close to the maximum, and scenarios where the incorrect node appears at various positions or depths. These constraints and edge cases will help guide your implementation. To solve LeetCode problem number 1660, the goal is to identify and remove the invalid node that disrupts the fully binary structure of the tree. The problem specifies that this invalid node is improperly connected to one of the nodes at the second to last level. This detail is crucial because it allows us to focus our solution on a specific part of the tree, rather than analyzing the entire structure indiscriminately. One approach to solving this problem is the brute force method, which involves a full traversal of the tree. In this approach, we analyze every node and check if any of its children violate the binary tree property by being incorrectly connected. For nodes at the second to last level, we would cross-reference their children with all other nodes in the tree to find inconsistencies. However, this method is inefficient. It has a worst-case time complexity of n squared, as every node may require comparisons with the rest of the tree. While conceptually straightforward, this brute force approach is impractical for larger trees due to its high computational cost. A more efficient solution to this problem is to use a breadth-first search, or BFS, traversal. The key insight here is that BFS allows us to process the tree level by level, which aligns naturally with the structure of the problem. Starting from the root, we explore each level of the tree systematically. When we reach the second to last level, we can check each node to see if any of its children have already been encountered during our traversal. This is achieved by maintaining a visited set, which keeps track of nodes that have been processed. If a child node is found in this set, it indicates that this is the invalid node. To correct the tree, we simply remove the invalid node by setting the appropriate left or right pointer of its parent to null. The BFS approach has a time complexity of O(n), since each node is visited only once, and a space complexity of O(w), where W represents the maximum width of the tree. This method is efficient, scalable, and directly addresses the problem constraints, making it an excellent choice for solving this challenge. Several key observations make the BFS approach particularly effective for this problem. First, the invalid node is at the leaf level, but it is improperly connected to a node at the second to last level. This specific placement allows BFS to isolate the second to last level naturally during its level-by-level traversal. Second, the use of a visited set enables constant time detection of the invalid node during the traversal, eliminating the need for additional passes. When comparing different strategies, the brute force method, while simple, is computationally expensive and unsuitable for large trees. Depth-first search, or DFS, could also solve the problem, but it complicates the process of isolating the second-to-last level and efficiently identifying the invalid node. In contrast, BFS offers a linear runtime, minimal space requirements, and a straightforward alignment with the level-based structure of the task. These advantages make BFS the optimal choice for solving this problem, striking the right balance between clarity, efficiency, and scalability. In this problem, we are tasked with correcting a binary tree that contains one invalid node. The invalid node exists on the second to last level of the tree and creates an incorrect connection by pointing to a node on the last level that is not its descendant. Our goal is to identify this invalid node and remove it, ensuring the binary tree regains its proper structure. To solve this, we use a breadth-first search, or BFS, approach. BFS allows us to traverse the tree level by level, making it ideal for identifying invalid connections in the second to last level efficiently. We start by initializing a queue for the BFS traversal. This queue will store each node along with its parent reference, which is crucial for making corrections later. Additionally, we maintain a scene set to track all visited nodes, helping us quickly detect duplicate connections. The first step is to add the root node to the queue, setting its parent to null since it has no parent. From here, we process the tree one level at a time, checking each node's children to determine if there are any invalid connections. If a child node is discovered to already exist in the scene set, this indicates an invalid connection. Specifically, it means the current node is pointing to a child that already has a valid parent, which violates the tree structure. When no invalid connection is found, we add the child nodes to the queue and mark them as seen, ensuring they are processed in subsequent levels. Once an invalid connection is identified, we move on to the correction step. Here, we update the parent node's pointer, either the left or right child, to null, effectively severing the invalid connection. After this correction is made, the binary tree is restored to its proper structure, and we return the root node as the corrected tree. Several key insights make this approach effective. First, BFS traversal is essential because it enables us to process the tree level by level, which aligns perfectly with the constraints of the problem. Additionally, tracking parent nodes ensures we can pinpoint exactly which pointer needs to be updated. Lastly, using a hash set for scene nodes allows us to detect duplicate references in constant time, ensuring the algorithm remains efficient. The two primary data structures that underpin this solution are the queue and the set. The queue is used for the BFS traversal, allowing us to process nodes level by level, and it stores tuples consisting of a node and its parent. The set, on the other hand, tracks all nodes that have already been visited. This set is crucial for detecting invalid connections, as it provides O(1) average time complexity for lookups. In terms of complexity, the time complexity of this solution is O(n), where n is the number of nodes in the tree. This is because each node is visited exactly once during the BFS traversal. The space complexity is also O(n), due to the memory required for the queue and the scene set. There are several edge cases to consider. For instance, if the tree has only one node, there are no invalid connections to correct. If the invalid node is the root, the algorithm should handle this scenario gracefully and return the corrected tree. Other edge cases include trees with deep levels but only one invalid connection, or trees without any invalid connections at all, in which case the original tree should simply be returned. Let's walk through an example to solidify our understanding. Consider the following input tree. The root node is 1, which has 2 children, 2 and 3. Node 2 has 2 children, 4 and 5. However, node 5 has an invalid right child pointing to node 3, which is not a descendant of node 5. To correct this tree, we start the BFS traversal at the root. At level 1, we add the root's children, 2 and 3, to the queue. Next, at level 2, we process node 2 and add its children, 4 and 5, to the queue. At level 3, we encounter node 5's invalid reference to node 3. Since node 3 has already been seen, we identify this as the invalid connection. To correct the tree, we update node 5's right pointer, setting it to null. After this correction, the tree is restored to its proper structure. The corrected tree has 1 as the root, with 2 and 3 as its children. Node 2 has 2 children, 4 and 5, and no invalid connections remain. This example demonstrates how the algorithm efficiently identifies and removes the invalid node, ensuring the tree is properly corrected. To solve the problem of correcting a binary tree, we start by importing the DEET class from the Collections module, which will help us perform a breadth-first search, or BFS, on the tree. Inside the correct binary tree method, the first thing we do is check if the root node is null. If it is, we simply return none, as there's no tree to correct. Assuming the tree is non-empty, we initialize a queue with the root node and a set called scene to keep track of nodes we've already visited. This will help us detect any invalid pointers. Using a while loop, we traverse the tree level by level. For each level, we process all nodes by iterating through them. As we dequeue a node, we first check its right child. If the right child is already in the scene set, it means we've encountered an invalid pointer. In that case, we call the removeNode method to remove the problematic node from the tree and return the corrected tree. If the right child is valid, we add it to the queue for further processing and mark it as seen. The same logic is then applied to the left child. If the left child is found to be invalid, we also call removeNode to remove the corresponding node and fix the tree. Otherwise, we add the left child to the queue and record it in the scene set. Once we've processed all the nodes at this level, the while loop continues with the next level until the queue is empty. At the end of this traversal, if no invalid nodes were found, the function simply returns the root of the tree, as no correction is needed. The removeNode method is a helper function that performs a BFS to find the parent of the target node that needs to be removed. As we traverse the tree, we check if the target node is a left or right child of the current node. Once we locate the parent, we set the corresponding pointer to none, effectively removing the invalid node, and return the updated tree. If no parent is found, the method returns the original root unchanged. This approach ensures that the tree is corrected efficiently while maintaining its overall structure. Here, we start by importing the necessary classes, including queue and set, which will help us perform a level order traversal and track visited nodes. We define our correct binary tree method, which takes the root of a binary tree as input. The first thing we check is whether the root is null, and if so, we return null immediately. This handles the edge case of an empty tree. Next, we initialize a queue to facilitate our breadth-first search and a hash set to keep track of nodes we've already seen. We then add the root node to the queue to begin our traversal. Inside the while loop, we process each level of the tree by iterating through all nodes at the current depth. For each node, we first check its right child. If the right child has already been visited and is in our set, this indicates that we've encountered an invalid pointer. In this case, we immediately call the removeNode helper method to remove the problematic node and return the corrected tree. Otherwise, we add the right child to the queue and mark it as seen by adding it to our set. Now, we perform a similar check for the left child of the current node. If the left child has already been seen, this means we've encountered another invalid pointer, and we again call the removeNode method to fix the tree. If the left child is valid, we add it to the queue for further processing and mark it as visited by adding it to the set. Once we've finished processing all nodes at the current level, we move on to the next level in the queue. If no invalid pointers are encountered throughout the traversal, we simply return the root node as is, indicating that the tree didn't require any corrections. At this point, the breadth-first traversal logic is complete, and we move on to the remove node helper function, which is responsible for disconnecting the problematic node from the tree. The remove node method takes the root of the tree and the target node that needs to be removed as input. We use a queue again to perform a level-order traversal of the tree. As we iterate through the nodes, we check if the current node's left or right child matches the target node. If it does, we disconnect the target node by setting the corresponding child pointer to null and then return the root of the tree. This effectively removes the invalid node and its subtree from the tree. If no match is found, we continue the traversal by adding the current node's left and right children to the queue, provided they are not null. Once the traversal is complete, we return the root node, ensuring the tree is corrected and intact. Finally, we include the definition for the treenode class, which represents the structure of each node in the binary tree. The treenode class includes 3 fields, an integer value val, and 2 pointers left and right that reference the left and right children respectively. We provide 3 constructors for flexibility: a default constructor, a constructor that initializes the node with a specific value, and a constructor that initializes the value in both child pointers. This class serves as the building block for the binary tree and is essential for implementing the solution. With this, the Java implementation of the correct binary tree function is complete, and we've covered the logic for identifying and removing invalid pointers in a binary tree. In this example, we have a binary tree where node 4 incorrectly points back to node 2, which is a sibling on the same level. Our goal is to remove node 3, the parent of node 4, to correct this issue. To start, we initialize a queue with the root node, which is 1, and an empty set called scene to keep track of nodes we have processed. At level 1, we dequeue node 1, process its children nodes 2 and 3, and add them to the queue. At this point, the queue contains nodes 2 and 3, and scene is updated to include these nodes. Next, at level 2, we dequeue node 2. Since it has no children, we move on to the next node in the queue, which is node 3. For node 3, we check its right child, node 4. Here, we find that node 4 points to node 2, which is already in our scene set. This indicates an invalid pointer. To fix this, we call the remove node function to remove node 3. The function traverses the tree to find node 3's parent, which is node 1, and sets its right child to none, effectively removing node 3. The final tree is now corrected, with node 1 as the root and node 2 as its only child. In this second example, we have a more complex binary tree where node 4's child, node 5, incorrectly points back to the root node 5. Our goal here is to remove node 4 to correct the tree structure. To begin, we initialize the queue with the root node, which is 5, and an empty scene set. At level 1, we dequeue node 5, process its children nodes 3 and 8, and add them to the queue. At this point, the queue contains nodes 3 and 8, and the scene set is updated to include these nodes. At level 2, we first dequeue node 3. We process its children, nodes 2 and 4, adding them to the queue and updating the scene set to include these nodes. Next, we dequeue node 8, which has no children, so we move on. At level 3, we dequeue node 2, which also has no children, and then proceed to node 4. For node 4, we check its right child, node 5. Here, we find that node 5 points to the root node 5, which is already in our scene set. This confirms an invalid pointer. To resolve this, we call the remove node function to remove node 4. The function locates node 4's parent, which is node 3, and sets its right child to none, successfully removing node 4. The final tree is now corrected, with node 5 as the root, nodes 3 and 8 as its children, and node 2 as the left child of node 3. In this edge case, the tree contains only the root node, which is node 1. Since there are no other nodes, there are no invalid pointers to address. The process is straightforward. We initialize the queue with node 1 and an empty scene set. At level 1, we dequeue node 1, but since it has no children, the traversal terminates immediately. The tree remains unchanged, with node 1 as the root. This approach effectively detects invalid pointers using a level-by-level breadth-first search. By checking if a child node points to a node already in the scene set, we can identify and remove problematic subtrees efficiently. The remove node function ensures that the invalid node is safely disconnected while maintaining the structural integrity of the binary tree. This method is both systematic and robust, making it well suited for correcting trees with invalid pointers. To analyze the time complexity of our solution, we start by considering the breadth-first search, or BFS, which is the core of our traversal approach. Here, every node in the binary tree is visited exactly once. This means that for a tree with n nodes, the BFS traversal takes n time. Additionally, when an invalid node is detected, the remove node function performs its own BFS to locate and remove the parent of the invalid node. In the worst-case scenario, this function might traverse the entire tree, leading to a time cost of n. However, since the remove node function is invoked only once during the entire process, its contribution remains additive. When we combine these two components, the BFS traversal and the single node removal, the total time complexity becomes n plus n, which simplifies to n. This demonstrates that the solution is efficient in terms of time complexity, even in the worst case. Now, let's examine the space complexity, which depends on the additional memory the algorithm uses during execution. First, consider the BFS queue. As the algorithm traverses the tree level by level, the queue temporarily holds nodes from the largest level of the tree. For a balanced binary tree, this largest level can contain roughly n/2 nodes, making the queue's maximum space usage proportional to n. Next, we have the scene set, which keeps track of all visited nodes to prevent redundant processing. In the worst case, this set will store all n nodes in the tree, contributing n to the space complexity. Finally, because the remove node function uses a queue for its traversal rather than recursion, there is no additional memory required for a recursive call stack. When we account for both the BFS queue and the scene set, the total space complexity sums up to n plus n, which simplifies to n. When we compare this approach to a brute force method, the advantages of our BFS-based solution become clear. A naive approach might involve iterating through every node and examining all of its children to identify invalid pointers. This could require multiple passes over the tree, leading to a time complexity of n squared in the worst case. In contrast, the BFS-based solution improves this to n by detecting the invalid node in a single traversal and removing it efficiently. This optimization is achieved by leveraging both the BFS traversal and the scene set, which allows us to track visited nodes without redundant checks. As a result, our approach not only minimizes the number of traversals but also ensures that both time and space complexities remain linear, which is the best possible outcome for this type of problem. Analyzing the best, average, and worst-case scenarios further highlights the efficiency of our approach. In the best case, the invalid node is located at the root or among its immediate children. Here, the BFS traversal terminates after just a few steps, and the remove node function operates on a very small subset of the tree. This results in a time complexity of 1 and a space complexity of 1. In the average case, the invalid node is situated somewhere in the middle levels of the tree. BFS traverses a portion of the tree, and the remove node function works on a moderate subset. Even in this case, the time and space complexities are n. Finally, in the worst case, the invalid node is found at the deepest level of the tree. BFS must traverse all nodes, and the queue size reaches its maximum. The remove node function also processes the entire tree. Despite this, the time and space complexities remain n, demonstrating the robustness of the solution under all scenarios. To solidify our understanding, let's consider the mathematical justification behind these complexities. The BFS traversal ensures that each node is processed exactly once, resulting in a traversal cost that scales linearly with the number of nodes, or n. Similarly, the remove node function processes nodes only once during its operation. Since this function is called only once in the algorithm, its cost adds to the total rather than multiplying it. This additive nature ensures that both time and space complexities remain linear in terms of n. By processing nodes efficiently and avoiding redundant operations, the solution achieves a level of scalability that makes it well-suited for large binary trees. In conclusion, the linear time and space complexities reflect the algorithm's ability to handle the problem in an optimal and efficient manner. In this problem, there are several common mistakes that can trip up even experienced coders. First, it's important to distinguish between BFS and DFS approaches. While DFS is useful for traversing trees, it's not ideal here because the problem requires identifying an invalid node that violates the tree structure. BFS, or level order traversal, is more suitable since it processes nodes level by level, ensuring that all nodes at the same depth are explored before going deeper. Another common issue is improper handling of parent pointers. When deleting the invalid node, failing to correctly update parent-child relationships can leave dangling references, leading to broken tree structures. Additionally, many solutions assume the input tree is balanced, but this problem doesn't guarantee balance. Algorithms must be robust enough to handle deeply skewed trees efficiently. Edge cases are another area that's frequently overlooked. For instance, what happens when the invalid node is the root or when the tree has just two nodes? Testing these edge cases is essential to avoid runtime errors. Lastly, inefficient node lookups can cause performance bottlenecks. If the solution repeatedly searches for nodes to verify connections, it could lead to O(n)² complexity. Using a hash set to track visited nodes ensures O(n) time complexity, making the solution more efficient. This problem is often seen in interviews because it tests your understanding of tree traversals and your ability to reason about tree structures. A key insight here is that BFS is generally preferred because it allows you to detect invalid nodes as soon as possible. This aligns with the problem's requirement to identify structural violations level by level. The problem also falls under the broader category of a tree correction or tree validation problems, which require you to identify and resolve structural issues, a skill that's valuable in many tree-related challenges. During interviews, you might be asked to discuss the trade-offs between BFS and DFS, particularly in terms of space and time complexity. You should also be prepared to explain how your solution minimizes auxiliary space or handles edge cases efficiently. Interviewers may pose follow-up questions, such as how your approach would adapt to additional constraints. For example, they might ask how you would preserve node values in a specific order or optimize for memory usage, so it's important to think critically about how your algorithm can be extended. To deepen your understanding of this problem, you can explore related problems that share overlapping concepts. For instance, LeetCode 105 focuses on constructing a binary tree from pre-order and inorder traversals, which reinforces your ability to build trees with a correct structure. LeetCode 98, on the other hand, deals with validating a binary search tree. This is a great way to practice identifying structural validity, which is closely related to the task of finding invalid nodes. LeetCode 133 is another useful problem, as it involves detecting and resolving invalid or incorrect connections in graphs, which parallels the idea of correcting structural issues in trees. Lastly, LeetCode 450 highlights the process of deleting a node in a binary search tree while maintaining its structure. This is particularly relevant because it focuses on ensuring that tree properties remain intact after modifications, which is a key aspect of the correct a binary tree problem. There are alternative approaches to solving this problem, each with its own trade-offs. Using DFS instead of BFS is one option. The advantage of DFS is that it tends to have a simpler implementation and uses less auxiliary space for recursive calls. However, it's less effective at detecting the invalid node quickly, as DFS may explore unnecessary paths before identifying the issue. Another approach is to use a hash map for parent tracking. This simplifies the process of reconnecting or removing nodes by explicitly maintaining parent-child relationships. The downside, though, is that it consumes extra memory for the hash map, which can increase space complexity. Finally, you could attempt an in-place correction without using extra data structures. This minimizes space complexity to O(1), which is ideal for memory-constrained environments. However, the code becomes harder to read and debug, and this approach may not scale well for large or unbalanced trees. Each method has its strengths and weaknesses, so the choice depends on the problem constraints and the priorities of your solution. Great job! We've successfully tackled LeetCode problem number 1660, correct a binary tree. We discussed the problem, implemented an efficient BFS-based solution, and analyzed its complexities. Remember, solving tree problems sharpens your algorithmic thinking. Thank you for joining, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!